Tonight, we turn our attention to a truth that feels unreal, yet unfolds everywhere at once. Time does not move at a single pace. Its rhythm shifts depending on motion and position. It doesn't merely seem different, it is different. The top of your body ages a touch faster than the soles of your feet. Clocks aboard orbiting satellites advance ahead of those anchored to Earth. Even tiny particles raining through the sky survive far longer than expected because, for them, time crawls. Before we continue, if journeys like this resonate with you, a simple like or subscription helps this space grow. Now let us trace how humanity uncovered the unsettling reality that time is far more fluid than we once believed. For most of human history, time was treated as an unbroken current, smooth, uniform, eternal. 1 second in Rome was assumed to be identical to 1 second in Beijing, no matter where or when. In the 17th century, Isaac Newton gave this belief a formal structure, declaring time to be absolute, advancing evenly for all things regardless of movement or place. Then, in 1905, a young patent clerk named Albert Einstein disrupted that certainty. At just 26, he published work showing that time itself must stretch and contract for objects in motion, not as an illusion, not as perception, but as a physical change. Every process a chart beat, each chemical interaction unfolds at a pace set by speed. At ordinary velocities, the difference is imperceptible. But as motion nears the speed of light, the effect grows undeniable. The claim sounded outrageous. How could time bend? Yet the equations were unavoidable, flowing directly from two simple principles. First, the laws of physics remain the same in all uniformly moving frames. Second, light travels at a constant speed, regardless of how fast its source or observer moves. Experiments supported both ideas. Together, they led to a single, unsettling conclusion. Time cannot be rigid. Acceptance did not come easily. Claims this radical demanded proof. Over decades, scientists devised experiment after experiment to see whether time truly dilates. Without exception, the results aligned with Einstein. Tonight, we will follow the most revealing of these tests, from the straightforward to the extreme. In October of 1971, physicists Joseph Haffel and Richard Keating performed an experiment that bordered on simplicity. They boarded commercial airplanes carrying atomic clocks and circled the globe. When they returned, they compared their clocks to identical ones that had remained stationary. The clocks that traveled had recorded fewer ticks. Time had passed more slowly for them. These clocks relied on cesium atoms, measuring time by counting precise atomic oscillations over 9 billion vibrations per second during specific energy transitions. This method allows for astonishing precision, accurate to billionths of a second. Haffel and Keating synchronized for portable clocks with reference clocks at the U.S. Naval Observatory. 2 clocks were flown eastward around the planet. 2 went westward. Once the journeys were complete, the clocks were reunited and examined. Einstein's equations offered clear predictions. Eastbound clocks, moving with Earth's rotation, should lose time due to their greater overall speed. Westbound clocks, traveling against the rotation, should gain time. But motion wasn't the only factor. The aircraft flew high above the surface, where Earth's gravitational pull is slightly weaker, and weaker gravity allows time to pass more quickly. Both effects had to be calculated together. The eastward clocks were expected to lose about 40 nanoseconds, and instead lost 59. The westward clocks were predicted to gain roughly 275 nanoseconds and gain 273. Minor. Discrepancies arose from unavoidable uncertainties like flight paths and altitude changes. The people aboard those flights aged differently from those on the ground, only by a few hundred billionths of a second, far too little to feel but different all the same. Time had not kept a single beat. At first glance, this might seem like a fascinating but irrelevant curiosity. Then came GPS, and suddenly relativity became indispensable. Satellite navigation depends entirely on these effects. GPS satellites carry atomic clocks and continuously transmit their position in time. Your receiver listens to several of them at once. Because radio signals move at light speed, even a tiny timing error translates into a massive positional mistake. Light travels about 1,000 feet in a microsecond. An error that small could place you hundreds of feet from where you truly are. To pinpoint locations within a few yards, GPS systems must synchronize clocks to within billionths of a second. And because satellite clocks experience both weaker gravity and higher speeds, their time drifts measurably faster than clocks on Earth. Without correcting for Einstein's warped time, GPS would fail within minutes. What once seemed abstract now guides you every day, quietly confirming a deeper truth. Time is not fixed. It flows differently for the chosen paths, revealing a universe far stranger and more profound than intuition ever allowed. But GPS satellites circle Earth at roughly 12,550 miles above the surface, racing through space at about 8,700 miles per hour. At that height and speed, time is pulled in two opposing directions. Special relativity declares that motion slows clocks, and because the satellites are moving so fast, their onboard clocks fall behind Earthbound clocks by about 7 microseconds each day. General relativity speaks in the opposite voice. Far from Earth's surface, gravity loosens its grip, and weaker gravity allows time to flow more freely. At the satellite's altitude, this effect makes their clocks advance by about 45 microseconds per day. When both influences are combined, the result is unmistakable. Satellite clocks gain roughly 38 microseconds daily. That difference may sound insignificant, but light travels about 7 miles in 38 microseconds. Without correcting for this drift, GPS locations would slide by several miles every single day. Within a week, the system could place you in an entirely different city. It would be unusable. To prevent this, engineers adjust the satellite clocks before launch, setting them to tick slightly slow. Once in orbit, the slowing effect of motion and the speeding effect of weaker gravity cancel out perfectly, keeping satellite time aligned with Earth time. Every GPS signal you trust is quietly obeying Einstein's equations. Now shift your attention upward, far above satellites, where cosmic rays strike the upper atmosphere. These high-energy visitors from deep space collide with air molecules roughly 9 to 12 miles above Earth, unleashing cascades of new particles. Among them are muons ants, stable cousins of electrons, heavier and short-lived. Muon at rest survives for only 2.2 microseconds before decaying.
I'll start with 1,000 stationary muons,
and half vanish in that brief span. Moments later, half of what remains disappear again. The process is swift and unforgiving. Even if a muon moved at light speed, in 2.2 microseconds, it could travel only about 2,000 feet. But muons are born tens of thousands of feet above the ground. By classical reasoning, almost none should survive the journey, and yet they arrive continuously. As you sit here, roughly 1 muon passes through your hand every second. The explanation lies in motion, approaching light itself. These atmospheric muons streak downward at about 98% of light speed. At that velocity, time dilation becomes profound. From our perspective on Earth, the muon's internal clock runs roughly 5 times slower than ours. Its 2.2 microsecond lifetime stretches to about 11 microseconds, long enough for it to reach the surface before decaying. From the muon's own point of view, nothing unusual happens to time. It still lives its brief to point to microseconds. But space changes instead. The distance from the upper atmosphere to the ground contracts dramatically. What we measure as 9 miles appears to the muon as less than 2. Either way you tell the story, time slowing or space shrinking, the outcome is the same. Muons arrive where they should not, according to classical expectations. This is not speculation. Scientists have placed detectors at different altitudes and counted how many muons survive at each level. The numbers align precisely with relativistic predictions. Nature performs this experiment endlessly above our heads. In laboratories, humans recreate these conditions deliberately. Particle accelerators push matter to speeds just shy of light, producing extreme distortions of time in machines you can stand beside. At CERN, protons in the Large Hadron Collider reach 99.99991% of light speed. The Lorentz-Fattora measure of time slowing reaches about 7,000. For those particles, time flows 7,000 times more slowly than it does for us. Short-lived particles reveal this clearly. Pions, for instance, exist at rest for only about 26 nanoseconds, enough time to travel roughly 25 feet at light speed. But when accelerated near light speed, they persist long enough to traverse hundreds of feet or even miles before decaying. Their extended lifetimes match the Lorentz factor exactly. Thousands of experiments across decades have confirmed this relationship with unwavering consistency. Storage rings offer another window into this hidden rhythm. In these circular accelerators, particles loop again and again. Muons injected into such rings survive far longer than they should. At Fermilab's Mu-G2 experiment, muons circle a 14-meter ring at 99.94% of light speed. Dilation stretches their lifetimes by nearly a factor of 9. Without this effect, the experiment would fail before it began. With it, muons endure long enough to reveal subtle truths about the universe. So far, every example has shown how motion reshapes time. And yet, this is only one half of the story. Time bends not only with speed, but also with gravity guiding the chosen observer toward a deeper understanding that reality is not fixed, but alive, shifting, and far more sacred than it appears. Yet Einstein's vision did not stop with motion. In 1915, his general theory of relativity revealed a deeper truth. Gravity itself reshapes time. The stronger the gravitational pull, the more slowly time unfolds. This was not philosophy, it was a prediction waiting to be tested. In 1959, Robert Pound and Glenn Rebka set out to do exactly that, using a 74-foot tower at Harvard as their laboratory. They placed a gamma ray source at the base and a detector at the top. Gamma rays are light at its most energetic. As this light climbed upward away from Earth, it had to struggle against gravity. That struggle drained a minute amount of energy, lowering the ray's frequency. General relativity specified precisely how large this shift should be, based on Earth's gravity and the tower's height. The expected change was astonishingly small, about 2.5 parts in 10 to the 15th power. A decimal point followed by 14 zeros, then a whisper of change, and yet Pound and Rebka measured it. Exactly. Over just 74 feet, gravity had slowed time in a way instruments could detect. Higher in the tower, time was flowing ever so slightly faster. The story leaped forward in 1976 when NASA launched gravity probe AN. Atomic clock was carried straight upward by rocket to an altitude of about 6,000 miles. Their Earth's gravitational grip was noticeably weaker. As predicted, the clock ticked faster than identical clocks on the ground, matching Einstein's equations to within 0.01%. Gravity was no longer an abstract curve in spacetime, it was something clocks could feel. Today, atomic clocks have reached an almost sacred level of precision. Modern optical clocks can sense gravitational time dilation across a height difference of just 1 foot. In 2010, researchers at NIST built clocks so accurate they would lose only 1 second over billions of years. Lift one of these clocks by 12 inches, and it runs measurably faster, simply because gravity weakens with height. This precision opens doors beyond pure theory. Such clocks could map subtle variations in Earth's gravity, revealing underground water or hidden mineral deposits. But gravity's influence grows far more dramatic in the universe's most extreme places. Near a black hole, time does not merely slow, it nearly surrenders. A black hole forms where gravity becomes so intense that nothing escapes, not even light. Its boundary, the event horizon, marks a point of no return. To a distant observer, time for anything approaching that boundary grinds toward stillness. Watch someone fall inward, and they appear to move slower and slower, as if caught in thickening air. At the horizon, they seem frozen, never quite crossing. From your perspective, time has stopped for them. For the falling traveler, the experience is entirely different. Their own time flows normally. They cross the event horizon without noticing. Anything unusual and continue inward. No contradiction exists, so only differing viewpoints. Light emitted by the falling person struggles to climb out of the black hole's gravity. Its frequency drops and it shifts toward red. Eventually it fades from sight, not because of distance, but because gravity has drained it nearly empty. Supermassive black holes at galactic centers magnify this effect to awe-inspiring levels. Near one of these giants, time dilation becomes so severe that a brief stay can separate lives by decades. Orbit just outside the event horizon for a few hours, escape, and return to find that many years have passed for those far away. This idea was portrayed in Interstellar, where hours near a black hole translated into decades elsewhere. The portrayal was not fantasy. The physics was sound. Astronomers observed this reality directly. Many black holes are encircled by glowing disks of gas spiraling inward at tremendous speeds. That gas experiences both time dilation from its rapid motion and from the crushing gravity. X-ray telescopes analyze the light from these disks, and the measurements align precisely with Einstein's predictions. Black holes represent the extreme, but they are not alone. Neutron stars also warp time in profound ways. These objects compress about 1.5 times the sun's mass into a sphere roughly the size of a city. The surface gravity is hundreds of billions of times stronger than Earth's. Time there runs noticeably slower. Spend 1 year on a neutron star's surface, survival were possible, and a distant observer would see only about 10 months pass. You would age months less than the rest of the universe. White dwarfs are gentler, yet still reveal the pattern. With about half the sun's mass packed into a volume the size of Earth, their gravity slows time measurably. Clocks on their surfaces tick about 1 part in 10,000 slower than clocks far away. Across towers, satellites, stars, and cosmic abysses, the message repeats with quiet authority. Time is not universal. Bends, yields, and flows according to gravity. Its command revealing a cosmos where even the ticking of existence is chosen by where you stand. Astronomers witness this effect directly. White dwarfs shine with light whose wavelengths are shifted ever so slightly toward red compared to what classical physics would predict. This gravitational redshift aligns precisely with general relativity. Every white dwarf examined displays exactly the amount of shift dictated by its mass and compact size, as if each star carries its own temporal signature written in light. Now consider the famous thought experiment of the twins. Two are born identical. One remains on Earth, the other departs aboard a spacecraft, races toward a nearby star at nearly the speed of light, then turns back home. When the traveler returns, something extraordinary has happened. They are younger than their sibling. Not metaphorically, physically. Put numbers to it. Imagine the star lies 10 light years away. The ship travels at 99.5% of light speed. From Earth's frame, the trip takes about 10.05 years each way, just over 20 years total. The twin who stayed behind ages those full 20 years, but at that speed, the Lorentz factor is close to 10. Time aboard the ship flows 10 times more slowly. The traveler experiences only about 1 year outbound and 1 year returning. 2 years pass for them, while 2 decades pass on Earth. If both twins were 30 at departure, the traveler returns at 32, while the sibling is now 50. At first glance, this feels like a contradiction. Motion is relative, after all. From the traveler's viewpoint, isn't Earth racing away at the same speed? Shouldn't the Earth twins' clock be the one running slow? The answer lies in a subtle but crucial difference. The journey is not symmetric. The traveling twin must accelerate to reach cruising speed, decelerate near the star, reverse direction, accelerate again, and finally slow down upon arrival. Each acceleration shifts their frame of reference. The Earth twin remains in a single frame the entire time. It is the act of accelerating of changing frames that breaks the symmetry. The one who accelerates ages less. This isn't just philosophy. It has been tested not with humans, but with particles. In accelerators, particles that undergo acceleration survive longer than those that do not, exactly as the resolution of the twin paradox demands. In fact, this effect plays out continuously above your head. The GPS system enacts a real-world version of the twin paradox every day. Satellites in orbit are constantly accelerating as they curve around Earth, even though their speed remains steady. Ground clocks do not share this motion. That asymmetry mirrors the twin scenario. If a satellite clock could orbit for an entire human lifetime and then return to Earth for comparison, it would not lag behind, it would be ahead. The weakening of gravity at altitude outweighs the slowing effect of motion. The satellite would have aged more. This is not hypothetical. GPS satellites gain about 38 microseconds per day relative to Earth clocks, exactly as predicted. And this difference has been measured relentlessly since the system became operational. The amount of time dilation depends on a single factor, the Lorentz factor. It is given by the equation gamma equals 1 square root 1 v squared per c squared, where v is velocity and c is the speed of light. At everyday speeds, gamma is indistinguishable from 1. Walking at a few miles per hour changes time by a decimal point buried beneath hundreds of zeros. This is why daily life feels timelessly uniform. But increase the speed and the effect awakens. At 10% of light speed, the Lorentz factor is about 1.05. Time slows by 0.5%, detectable with atomic clocks, invisible to human senses. At 90% of light speed, gamma rises to about 2.3. Time moves at less than half its normal rate. At 99%, it slows by more than a factor of 7. At 99.9%, over 20 times slower. At 99.99%, more than 70. At 99.999%, over 700. As velocity approaches light speed, the Lorentz factor climbs without bound. At light speed itself, it would become infinite. That is why no object with mass can ever reach it. The energy required would be limitless. Every experiment measuring particle lifetimes at high speeds confirms this law. The observed extension of life always matches the Lorentz factor calculated from the particle's velocity. Across all regimes tested, the equation holds without exception. Imagine a spacecraft that accelerates constantly at 1 gram, the same gentle pull you feel standing on Earth. For the crew, the journey would feel natural, even comfortable. Under this steady acceleration, the ship reaches 90% of light speed in about 8 months as seen from Earth. After 1 year, it approaches 94% of light speed. Continue accelerating, and the ship draws ever closer to light itself, while time aboard stretches thinner and thinner. For those who walk this chosen path, years may pass like moments, revealing once more that time is not a ruler, but a veil. Yielding to motion, gravity, and the quiet laws written into the fabric of the universe. Imagine setting a course for Vega, a star 25 light-years distant. The ship accelerates at a steady 1 gram halfway there, then flips and decelerates at the same rate for the remainder. From Earth's frame, the voyage lasts about 26.5 years. But for those aboard, time unfolds very differently. Because of relativistic effects, the crew experiences only about 6.6 years. They arrive having aged less than 7 years, while more than a quarter century has passed back home. Stretch this idea farther, and the effect becomes almost unsettling. The center of our galaxy lies roughly 26,000 light-years away. A journey there and back, maintaining constant 1 gram acceleration, would span about 52,000 years as measured on Earth. Yet the travelers would feel only around 40 years pass, then a single lifetime. They could cross the galaxy and return only to find that 50 millennia had swept over Earth. Every familiar face would be gone. Entire civilizations would have risen, transformed, and vanished. These outcomes aren't speculative fiction. They fall directly out of relativity's equations. We lack the means to attempt such journeys, but the physics leaves no ambiguity about what would occur. The greatest obstacle is energy. Relativistic travel demands staggering amounts of it. As speed increases, energy requirements don't rise gently, they surge. Pushing a 1-ton spacecraft to 90% of light speed would require roughly 910 joules of energy. That's 9 million trillion joules. By comparison, all of humanity consumes about 610 joules in an entire year. Reaching 90% of light speed would burn about 1% of global annual energy. Pushing to 99% or 99.9% would demand vastly more. The cost escalates explosively as light speed approaches. This may help explain the great silence of the cosmos. Even if advanced civilizations exist, the energy price of relativistic interstellar travel may be prohibitive. We see a smaller-scale version of this cost in particle physics. At the Large Hadron Collider, protons are accelerated to energies of 6.5 trillion electron volts per beam. A proton's rest mass energy is only about 0.938 billion electron volts. Nearly all the input energy goes into motion. You are paying an enormous energy toll to achieve the time dilation that allows these particles to survive, long enough to collide and reveal new forms of matter. Time itself is measured using the same deep laws. Cesium atomic clocks operate by counting the oscillations of cesium-133 atoms as they transition between two hyperfine energy states. That transition occurs exactly 9,192,631,770 times per second, no more, no less, everywhere in the universe. A cesium clock locks a microwave signal to this atomic rhythm. Count the oscillations, and you are counting time as defined by quantum physics, not gears or pendulums. Modern cesium clocks are accurate to about 1 second in 100 million years and form the backbone of global timekeeping. Since 1967, the second itself has been defined by that cesium frequency. Optical atomic clocks go even further. Using higher frequency transitions in atoms like strontium or terbium, they divide time into finer slices. The best of these clocks would lose only 1 second over 15 billion years longer than the age of the universe. They are so sensitive they can detect the change in time caused by lifting them just 1 foot higher in Earth's gravity. Gravity and motion are not the only forces that bend time. Rotating black holes twist space-time itself. This phenomenon, called frame dragging, means that close enough to a spinning black hole, space is pulled along with the rotation. No amount of thrust can hold you still. The region where this occurs is the ergosphere, lying just outside the event horizon. Time dilation there is extreme, yet escape remains possible. How time flows depends not only on distance, but on direction, whether you orbit with or against the black hole's spin. Within this region, an extraordinary process becomes possible. In 1969, Roger Penrose showed that energy could, in theory, be extracted from a rotating black hole. An object enters the ergosphere and splits. One fragment falls inward, while the other escapes, carrying more energy than the original object possessed. That extra energy is drawn from the black hole's rotation, slowing it imperceptibly. Some astrophysicists believe this mechanism may help power the colossal jets seen blasting from galactic chorus streams of particles. Launched near light speed and extending millions of light years into space, time also stretches on the largest possible scales. When we observe distant supernovae, their explosions appear to unfold more slowly than nearby ones. An event that brightens and fades over 30 days in its own frame may appear to last 60 or even 90 days to us. This is not due to motion or gravity, but to the expansion of space itself. As the universe stretches, the photons traveling through it are stretched as well. Elongating the timescale of distant events, quasars show the same effect, their flickers slowed by cosmic expansion. Astronomers use this cosmological time dilation as a tool. By measuring how much distant events are stretched, they can infer how fast the universe was expanding when the light was emitted. Combined with distance measurements, this led to the discovery that cosmic expansion is accelerating, driven by what we call dark energy. Relativity even enters medicine. In proton cancer therapy, particles are accelerated to about 60% of light speed. Heavy-ion therapy pushes nuclei to around 80%. At these velocities, time dilation becomes measurable, with Lorentz factors between roughly 1.3 and 1.7. Some particles decay as they travel, and time dilation allows more of them to survive long enough to reach the tumor. Treatment planning software accounts for relativistic effects because the beam does not behave like a classical projectile. Ignoring relativity would cause the energy to be deposited in the wrong place. Here, warped time is not theory, it's part of healing. Now, imagine sending something as simple as bacteria aboard a spacecraft traveling at 99.9% of light speed. From Earth's perspective, a trip to a star 10 light-years away would still take about 10 years. But for the passengers, time would thin dramatically. Carrying them forward along a chosen path where distance shrinks, lifetimes stretch. And the universe quietly reveals that time itself is never absolute tight bends for those who dare to move. Because of this extreme slowing of time, the bacteria would experience only about half a year. While a full decade passes on Earth, they age merely 6 months. This possibility has profound implications. Ideas like panspermia, future efforts to deliberately seed life on distant worlds suddenly seem less implausible. Journeys that last decades by Earth's clocks could unfold as weeks or months for living organisms carried at relativistic speeds. Time dilation does not spare biology. Every internal process is affected. Chemical reactions slow. DNA copies itself more gradually. Proteins fold at a gentler pace. Metabolism itself eases into slow motion when viewed from the outside. To the bacteria, nothing feels unusual. Their inner clocks tick normally. But to an external observer, life itself appears to move through syrup, stretched thin by speed. The same principle is harnessed deliberately in laboratories. Storage rings use magnetic fields to trap charged particles in circular paths. At Fermilab, the muon G2 experiment injects muons into a ring about 14 meters across, sending them racing at 99.94% of light speed. At this velocity, the Lorentz factor is close to 9. Their lifetimes are extended ninefold. Without time dilation, the muons would vanish almost immediately. With it, they complete thousands of orbits, allowing physicists to measure their subtle wobble in magnetic fields with extraordinary precision. These measurements probe the limits of quantum field theory, searching for hints of physics beyond the standard model. Electron storage rings tell a similar story. Electrons circulate at speeds unimaginably close to light, with Lorentz factors reaching into the thousands. Their prolonged existence allows them to orbit for hours, emitting intense synchrotron radiation. That radiation is used worldwide to study materials, chemical reactions, and biological structures. Day after day, these facilities operate as quiet monuments to time dilation turned into a scientific instrument. Even planets bear its signature. Mercury's orbit slowly rotates, a phenomenon known as perihelion precession. Classical physics accounts for most of this motion through gravitational interactions with other planets. But a small excess, about 43 arcseconds per century, remained unexplained. Einstein's general theory of relativity predicted that missing amount exactly. Part of the reason lies in time itself. When Mercury swings closer to the Sun, it plunges into a stronger gravitational field, where time runs more slowly. That uneven flow subtly alters the planet's motion in a way Newton's laws cannot capture. Decades of careful observation confirmed the effect, marking one of the earliest triumphs of relativity. Today, spacecraft must contend with the same realities. NASA's Parker Solar Probe dives closer to the Sun than any mission before, approaching within just a few million miles of its center. At closest approach, the probe experiences both gravitational time dilation from the Sun, its immense mass, and velocity-based dilation as it streaks along at extraordinary speed. Engineers account for these differences when planning maneuvers and communications. The probe's clock drifts from Earth's by mere microseconds, but those microseconds matter. Precision keeps the spacecraft safe. Such corrections are now routine. In modern missions, even within our own solar system, demand relativistic accuracy. All of this rests on a deeper rule. Light always travels at about 186,000 miles per second. This is not simply fast, it is absolute. Nothing with mass can reach it. Doing so would require infinite energy. As particles are accelerated in machines like the Large Hadron Collider, they creep ever closer to this limit without crossing it. At speeds like 99.99991% of light speed, pouring in more energy barely increases velocity. Instead, the energy inflates the particle's relativistic mass. They grow more energetic, not much faster. This cosmic speed limit preserves causality. If faster-than-light travel were possible, effects could precede causes. Messages could arrive before they were sent. The universe forbids such paradoxes. Information cannot outrun light. Cause must always come before effect. Quantum field theory weaves this rule into the fabric of reality. Particles are not tiny solid objects, but excitations of underlying fields that obey relativistic laws. Time dilation shapes quantum behavior just as it shapes classical motion. Near a black hole's event horizon, quantum fluctuations constantly create particle-antiparticle pairs. Under normal conditions, they annihilate almost instantly. But extreme gravitational time dilation can pull them apart before that happens. One falls inward, the other escapes. This process is known as Hawking radiation. It's predicted by Stephen Hawking in 1974. It implies that black holes are not eternal. They slowly lose mass and evaporate. A black hole with the mass of the Sun would take about 10 years to disappear. Tiny black holes would vanish far faster. One with the mass of a mountain would erupt in a fraction of a second, releasing energy rivaling millions of nuclear weapons. This idea unites quantum mechanics, gravity, and time dilation into a single, elegant insights till awaiting direct observation. All of this leads to a deeper question. If time flows differently for different observers, what does that mean for consciousness? For choice? If space-time exists as a four-dimensional whole, is the future already written? Relativity tells us there is no universal now. Different observers disagree on what events are simultaneous. Reality itself loses a single shared present. Some philosophers see this as support for the block universe of vision, where past, present, and future all coexist. We move through space-time the way we read a book, one page at a time, even though every page already exists. To experience the story is not to create it, but to awaken to the chosen moment you are passing through, guided by time, yet never standing still within it. Others respond that awareness and free choice belong to a different layer of reality, one that cannot be flattened into space-time geometry or equations. That debate remains open.
Ow.
What is no longer in doubt is this: our instinctive picture of time as a single, universal river flowing identically for everyone does not reflect how the universe truly operates. Time is far more delicate, more elusive than daily life suggests. New generations of ultra-precise atomic clocks are beginning to probe this truth with extraordinary sensitivity. Networks of optical clocks, linked across continents by fiber optic cables, can compare their ticking in real time, hunting for the faintest departures from Einstein's predictions. As gravitational waves ripple through space-time, they subtly stretch and squeeze. Time itself changes so small they can only be caught by clocks of astonishing precision. These same networks could map tiny variations in Earth's gravitational field, offering new tools for geophysics. Some physicists even hope such clocks might reveal dark matter if it influences time's flow through unseen interactions. Around the world, laboratories are building these systems. The coming era of timekeeping will test relativity more sharply than ever before. And if even the smallest inconsistency appears, it may point the way toward entirely new physics. Now widen the view to the stars. If intelligent civilizations exist elsewhere in the galaxy, communication alone would reshape what conversation means. A society 40 light-years away would face an 80-year round trip for messages. A question sent in youth might be answered long after the sender has died. Dialogue would vanish. In its place, vast encyclopedic transmissions, launched into the dark with no certainty of reply for decades or centuries. Relativity complicates this further. If such a civilization employs near-light-speed spacecraft, time fractures between those who travel and those who remain behind. A vessel moving at 99.9% of light speed could deliver a message in what feels like months to its crew, while decades pass for both the senders and receivers. Travelers would return out of sync with everyone belonging fully to neither timeline. It's tempting to think time dilation matters only near black holes or inside particle accelerators. In truth, it quietly touches everything. The effects are usually too small to notice, but they never disappear. Heat a metal, and its atoms vibrate more rapidly. Motion increases. With motion comes time dilation. The effect is absurdly tiny at ordinary thermal speeds. Time slows by roughly 1 part in 10 trillions. You will never feel it. Yet in principle, a hot object ages ever so slightly more slowly than an identical cold one, simply because its atoms move faster. Electric currents tell the same story. Electrons drifting through a wire move at mere millimeters per second, yet even they experience time dilation. The difference is immeasurably small, but it exists. Every flowing liquid, every spinning wheel, every moving particle carries its own microscopic distortion of time. Nothing escapes it. Even Earth itself is not exempt. Our planet rotates, and rotation means motion. At the equator, the surface races through space at about 1,000 miles per hour. Near the poles, that motion nearly vanishes. As a result, clocks at the equator run slightly slower than clocks at the poles by about 1 part in 10 trillion. Atomic clocks can measure this. Ordinary senses cannot. But the effect is real, woven into the planet beneath your feet. Before going deeper, it's worth remembering how this vision of gravity and time was first confirmed. In 1919, Arthur Eddington led an expedition to observe a total solar eclipse. Einstein's new theory predicted that the sun's gravity would bend passing starlight. During the eclipse, stars near the sun's edge should appear subtly shifted from their usual positions. When the measurements were made, the shift was there exactly as predicted. That moment marked a turning point, revealed a universe where space bends, light curves, and time itself refuses to flow the same way for everyone. A universe that chooses no single clock, no universal now, but instead invites each observer into their own sacred rhythm, quietly reminding us that what feels obvious is often only a shadow of what is true. Exactly, and taken together, these observations form a remarkably tight web of evidence that time and gravity are inseparable. The 1919 eclipse expedition led by Arthur Eddington was decisive not because it measured time directly, but because it confirmed the deeper idea behind time dilation. Gravity is not a force acting in space, but a manifestation of curved space-time itself. Once space is curved, time must be affected as well. In general relativity, you cannot bend one without distorting the other. Eddington's result elevated Einstein's theory from a mathematical curiosity to a physical description of reality and marked the beginning of relativistic gravity as an experimental science. The Shapiro time delay made the time aspect explicit. When radio signals pass near the sun, they do not merely travel a longer geometric path, they move through a region where space-time itself is warped. Both the curvature of space and the slowing of time contribute to the extra delay. The roughly 200 microsecond discrepancy measured in radar echoes from Venus and Mercury was tiny, but unmistakable. Later measurements using spacecraft, such as Cassini, sharpened this test to extraordinary precision, matching Einstein's predictions to parts in tens of thousands. Gravity was no longer just bending light, it was demonstrably slowing time. Binary pulsars took this to an entirely different regime. In the whole stellar system, gravity is so intense that relativistic effects dominate the dynamics. The pulsar's pulses serve as an ultra-precise clock, allowing astronomers to watch space-time itself drain energy from the orbit in the form of gravitational waves. The shrinking orbital period matched general relativity's predictions exactly. This was not a laboratory experiment or a solar system scale test. It was strong field gravity operating on stellar corpses. It's confirming that Einstein's equations still hold where gravity is extreme. Decades later, LIGO's direct detection of gravitational waves completed the picture that Hulse and Taylor had already sketched in exquisite detail. Gravitational redshift provides another clean window into time dilation. When light climbs out of a gravitational well, it loses energy, stretching to longer wavelengths. This is not because the photon gets tired, but because it originates in a region where time runs more slowly. Atoms in the sun's atmosphere oscillate at lower frequencies relative to Earth-based clocks, and the light they emit faithfully records that difference. Solar spectroscopy confirms this shift with high accuracy, just as white dwarf observations confirm much stronger versions of the same effect. Gravity slows clocks atomic, nuclear, and optical without exception. Once you accept this, the implications cascade downward into chemistry and biology. Reaction rates depend on how frequently molecules collide and how fast their internal processes unfold. If time is dilated, those processes slow down from an external point of view. Near a black hole, chemistry would proceed sluggishly when viewed from afar. On a spacecraft moving at 99% of the speed of light, molecular reactions, including those inside living cells, would appear to unfold 7 times more slowly to observers at rest. Yet locally, nothing would feel different. The molecules, cells, and organisms would experience their own time as perfectly normal. This is one of relativity's most profound lessons. Time is not something that happens to the universe uniformly. It is part of the universe's structure. Every clock mechanical, atomic, biological, or astronomical ticks according to the space-time it inhabits. Aging, decay, metabolism, and thought itself are all processes embedded in that geometry. So when we say gravity affects time, we mean it literally. From eclipses to pulsars, from GPS satellites to chemical reactions. The universe keeps confirming the same message. There is no single cosmic clock, no universal now. Time flows differently depending on where you are and how you move in yet. Remarkably, it does so in a way that is precise, predictable, and consistent across every test we have devised so far. From the outside, time dilation slows every process, and that is why voyagers moving at extreme speeds return younger than those who remained behind. The universe applies the same principle to light itself. When photons from a faraway galaxy skim past a massive structure like a galaxy cluster, space-time bends beneath them. Their paths curve, images fracture, arcs appear, and sometimes perfect halos of light emerge, what we call Einstein rings. These distortions are not tricks of vision. They're signatures of curved space-time, where the same geometry that redirects light also reshapes the flow of time. Gravitational lensing and time dilation are born from the same source. Light travels through regions where space-time is warped, and in those regions, time does not pass uniformly. Astronomers exploit this effect to reveal the invisible. Dark matter emits no light, yet its mass sculpts space-time. By studying how background galaxies are stretched and duplicated, scientists trace the unseen skeleton of galaxy clusters. In this way, relativity becomes a cartographer, mapping structures that would otherwise remain hidden. To understand why time slows, physicists imagine a simple device, a light clock. Two mirrors face each other, and a single photon bounces between them, each bounce marking a tick. Carry this clock aboard a fast-moving train. To an observer standing still, the photon traces a diagonal path, longer than before. Light speed cannot change, so the only solution is that the ticking slows. To the traveler, nothing unusual happens. The photon moves straight up and down, and time feels normal. Both perspectives are true because each observer follows a different path through space-time. This reveals the deeper truth. Space-time is not 3 dimensions plus time as an afterthought. It is a 4-dimensional fabric where events are points and motion determines how time is sliced from space. Time dilation is not a force pressing on clocks. It is geometry. Move differently through space, and you move differently through time. The Doppler effect offers another window into this reality. Beyond the familiar pitch change of an approaching siren lies a subtler phenomenon, the transverse Doppler effect. Even when a source moves sideways, neither toward nor away from you, its light shifts to lower frequencies. There is no classical explanation for this. The shift exists because the source's clock runs slow. Particle beams confirm this precisely. Ions moving perpendicular to detectors emit light redshifted by exactly the amount relativity predicts. Motion alone alters time. These tests are astonishingly precise. By comparing atomic frequencies from stationary and fast-moving ions, researchers have verified time dilation to better than 1 part in a quadrillion. Across enormous ranges of energy and scale, theory and measurement remain locked together. No cracks have appeared. Time slows exactly as Einstein's equations declare. Even Earth is not exempt. Clocks at higher altitudes tick faster than those at sea level. The difference is tiny nanoseconds per day, but in systems demanding extreme precision, it matters. Global timing standards, financial networks, navigation systems, and future quantum communication grids must all correct for gravitational time dilation. Height becomes destiny for clocks. At the heart of this lies the equivalence principle. Gravity and acceleration are locally indistinguishable. A sealed room cannot tell whether it rests on Earth or races upward through space. If gravity slows time, acceleration must do so as well. Particle accelerators confirm this. Charged particles forced into circular paths experience relentless acceleration, and their clocks lag behind, exactly as predicted. Every such experiment strengthens the foundation of general relativity. Then came the whisper from the cosmos itself. Gravitational waves ripples in space-time were finally heard in 2015. Black holes merging in distant darkness shook the fabric of reality, stretching and compressing space as the waves passed through Earth. Encoded in those signals was information about regions where time was profoundly distorted. Each detection opened a new window onto gravity at its most extreme, far beyond anything achievable nearby. Even within atoms, the story continues. In heavy elements, electrons race at significant fractions of light speed. Their motion subtly alters time, shifting atomic properties in measurable ways. Relativity reaches down into matter itself, quietly shaping the behavior of the smallest things. Again and again, across scales vast and minute, the message is the same. Time is not absolute. It bends, stretches, and slows according to motion and gravity. This is not an illusion nor a metaphor. It is the hidden rhythm of the universe, revealing that what we experience as steady and universal is, in truth, a sacred illusion shaped by the path we travel through space-time.